Hi, and welcome to Allen High School's discussion of electrochemistry at the AP-IBHL level. We are in the process of trying to determine whether a cell we created would proceed spontaneously, meaning there would be no thermodynamic barriers, or non-spontaneously, meaning there are some barriers and we're going to have to provide a push or a power supply for electron movement. Now, I'm going to be discussing 3 ways that we can do that. And one of them is a qualitative way by looking at a chart. So let me introduce that chart. You would have that chart for AP. You would have that chart on the free response, but not likely on the multiple choice. So it's important that you understand the signs and the concepts of that. Now, we call that chart a standard reduction potential. So we have 3 key words here: standard, reduction, potential. A standard is an agreed upon convention, and scientists, not surprisingly, agreed that the partial pressure, if it is a gas, should equal 1 atmosphere, or 101.33 kilopascals. If it is a solution, not surprisingly, remember we use those brackets to mean molarity. So if we have some sort of aqueous solution, the agreed upon standard is 1 molar. And it is standard ambient temperature and pressure. We're going to link this to our free energy very quickly. Remember, delta G naught is our measure of spontaneity, whether we've got energy available to do work. And so we're going to use standard ambient temperature, and that's 25 degrees Celsius. So that's what the word standard means. Reduction is, these have all been compiled as reduction half reactions. Now, it's going to be very, very handy because if it's an oxidation half reaction, so if we have oxidation, all we're going to need to do is change the sign. So there's really no reason to have both tables. I remember when I was in school, we had a reduction table on one side and an oxidation table on the other side, and that's a little redundant because oxidation is simply the opposite of a reduction. So we're going to be changing the sign. Now, if we're going to measure reductions, you can't have a half without a whole. It's like the old song, love and marriage go together like a horse and carriage. Well, reduction goes together with oxidation. So we always have to measure these against another half reaction. And the half reaction that has been agreed upon is called the standard hydrogen electrode. And I'm going to show you that in just a minute. The standard hydrogen electrode, also fondly known as She. So we're going to measure this against She. I don't know if that makes sense, like vocabulary-wise or grammatically speaking, but that's its little acronym, the standard hydrogen electrode. Well, what's a potential? A potential involves some sort of a possibility. And here we have the possibility of an electromotive force. So it's a force or a potential for movement. So it's also called the EMF. We used a capital letter E for this, often done in kind of a cursive. And it's the drive for our movement of electrons. So is there a spontaneous drive? In other words, is it going to be going to a more stable system? Or is this something we're going to have to provide energy for? So we measure this in volts. It's a potential, an electromotive force is in volts. And if we have E naught, that means it's standard. If we have E, that will be for non-standard. In other words, maybe not 1 atmosphere or maybe not 1 molar or possibly a temperature other than 25 degrees Celsius, so non-standard. Now, as our potential becomes more positive, so as it becomes more positive, the substance has a greater tendency to become reduced. So if you're comparing two and you want a spontaneous, if you're comparing two half reactions and you want a spontaneous system, you want the most positive to be reduced. And if you want a non-spontaneous situation, I usually figure out what spontaneous would be and then do the opposite. You want the most positive to do what it doesn't want to do, and that means to be oxidized. The more negative our E naught, the greater the tendency to become oxidized. All right, so let's take a look at that in a little bit more detail. We're going to look at that standard electrode, that standard hydrogen electrode, and the reduction potential table in our next video. So until then, this is signing off.